Welcome back! Today we are diving into a core skill everyone working with databases must master. Equality conditions in the where clause. This looks simple on the surface, but a tiny mistake in the index order can force the database to read thousands of unnecessary rows. Let's cover the common traps, especially gaps in the index prefix, and learn how to avoid them. Hi, I'm Jakub from DB Booster Academy. Let me introduce my sample table. It contains movies. The columns are ID, the primary key, movie name, country of origin, score from 0 for the worst movie to 100 for the best one, language, and a few additional columns. Let's start with how databases actually builds and index from existing data. Imagine I run this command, create index on movies for language, score, and name. Behind the scenes, the database first creates an internal query that selects only the columns used in the index, in this case, language, score, and name. And it also needs a reference to the actual table rows. In my case, row ID. Because index data must be sorted, the database needs order by clause. You might be wondering why this query matters. The key point is that this query represents what we call the index leaf level. The leaf level contains exactly same data ordered in the same way as this query. The only difference is that the data is split into pages. Splitting the data is a simple task. The database simply reads one row after another, fills the index pages in this sorted order, and whenever page becomes full, it allocates a new one and links it to the previous page. This continues until all rows are processed and we end up with the entire leaf level, ordered and connected in double linked list. To build the next level above, the database takes the highest key value from each leaf page, store it in a new page, and adds pointer back to it. Once that intermediate level is complete, the database builds the next level above it in the same way. This process repeats for each higher level until finally there is only one page left, and that page becomes the root of the index. So in the end, the database builds the full B-tree structure. But today we don't need to explore the entire tree. We'll focus mainly on what happens at the leaf level. To make things easier to visualize, I'll use the result of this select query instead of drawing the full index tree. So for the index on language, score, name, I'll just represent the data in the simple table view using those columns. And to keep it even simpler, I'll skip the row ID for now. Let's move to include. First of all, it's not supported in Oracle. Include allows you to add extra columns into the index. Columns that are stored in the leaf pages but not used while traversing the tree. They are not sorted and they don't affect the search path. Let's check the query behind the create index command. If I move the columns score and name from the indexed part into include section, they disappear from the order by clause of the internal index query. You can verify the result and see that the data are still sorted by language, but score and name are no longer ordered. For example, for movies in Arabic, I have scored 10 and then 6. Include is useful when you need to store additional columns that are not used for searching and you don't care about their order. Since they are not used in intermediate levels of the B tree, you save space and sometimes even reduce the overall height of the index. In practice, it's often used to make an index covering so that the query can be fully satisfied from the index without going back to the table. Sometimes I really wish Oracle had this feature too. Let's start with the where clause scenarios. I have an index for language, score, and name. On the slide, you can see the table that represents the leaf level. Now I want to search using a single equality condition, language equals Bengali. Because language is the first column of the index, the database can use an index range scan, also called index seek. It traverses the tree to the first occurrence of the Bengali movie, and then scan phase reads the next Bengali rows that follow in the leaf pages. In fact, this search is identical to adding the where clause to the query that built our leaf view. This returns exactly Bengali rows we expect. However, I cannot use an index range scan for conditions like score equals 50 or name equals troll hunter. That's because score and name are not the leading columns of this index. With a single equality predicate, a range scan is available only when the predicate is the first column of the index. If the first column is not used, the optimizer has two options: index skip scan, if the database supports it, or index full scan. Keeping the same index, I'll change the where clause to language equals English and score equals 61. I have exactly 50 rows matching these filters. Now, the key question is the index on language, score, name the best choice here? Or would score, language, name be better? Let me show you the two leaf level views. They look different. The first one starts with Arabic 6, Huda's Saloon, The second shows 0, English, and Family's Secret. But when I perform the search, that is, when the database seeks to the first row matching language equals English and score equals 61, both indexes land on rows with the exact same key values, as name is ordered to. And the next 49 rows are the same set as well. Just the order of columns differ. In both trees, we dive into different pages because the ordering is different, but we still arrive at the exact same row. As the data volume is the same, the tree height is the same, so the number of I/O steps to reach the first match is effectively the same. After that, I scan the remaining 49 rows, again the same work. There is a small wrinkle. Sometimes those 50 rows might span 2 leaf pages in one index and fit into 1 leaf page in the other. That's just page boundary lag based on your data, distribution, and filters. In general, the total work is the same. Conclusion: for a query that uses pure equality on both first 2 columns, it doesn't matter whether you put language first or score first in the index. For this use case, both indexes range scans do the same amount of work. Using the same equality conditions, let's compare 2 indexes. The first one is ordered by language, score, and name, and the second one is ordered by language, name, and score. As you can see, I only switch the last two columns. Both indexes can use an index range scan, called index seek in SQL Server, but the performance will be drastically different. With the first index, the database traverses the tree and reads exactly 50 rows, and all 50 satisfy both conditions. With the second index, the database also traverses the tree, but only using language, the first column. So it finds the first movie in English and then continues scanning all English movies, filtering out every row where the score is not 61. And there are 7,406 English movies. A huge difference, 50 rows versus 7,406 rows. This is a performance trap. Even when you see an index range scan in the execution plan, you must always check whether there is a gap in the index prefix. In my example, I used language in the condition, and language is the first column of both indexes. So for both indexes, an index range scan can be used. But in the first index, the next column is score, which is also used in the condition. So the index can use both language and score to traverse the tree. However, in the second index, the second column is name, and score is the third column. Since it's crucial to understand why the database cannot traverse the tree using the score column, let me show you a small excerpt of the index for English movies. You can see that the Pinocchio was filmed several times. The index is sorted by language first, so inside each language, movies are grouped by title, not by score. That is why the score cannot be used for navigation. The database cannot jump directly to score 61. The score is ordered only within each group of the same movie name. All the Pinocchios are grouped together, and inside that group, the ordering by score works fine. However, as soon as we jump to another movie, for example Pinocchio 3000, the ordering by score starts from the beginning again. So, as you can see, there is no other option than scanning all English movies and checking the score for every single one of them. That means score is not part of the index prefix. The database traverses only by language, and score is used only later to filter out rows that do not match after reading thousands of them. Oracle and SQL Server distinguish these conditions. Oracle calls the conditions used for tree traversal access predicates, and the ones used to filter rows filter predicates. SQL Server calls them seek predicates for traversal and simply predicates for filtering. Unfortunately, PostgreSQL does not show you this difference. You just see an index scan with all the conditions listed. As I said, this is a trap. You have to check whether the index prefix matches your conditions, even if you see an index range scan or index seek in SQL Server. This is a very common tuning mistake. People see an index range scan and immediately assume that it must be the optimal access path. But it's not necessarily true at all. And again, remember the difference in my example. 50 rows versus 7,406. That is a massive difference. Similar trap is when you have the right order of columns in the index, but some of them are in the include part of the index. Let's assume an index on language with score and name in the include section. If the condition is language equals English and score equals 61, the index range scan can be used because language is the first column. But score is included, which means 1. Score is not part of the intermediate levels of the index, so it cannot be used for traversing the tree. 2. Score is not sorted in the leaf level. Because score cannot be used for navigation, the database will find the first movie in English and then read all other English movies, and only then filter rows where the score is not 61. So again, I end up reading 7,406 rows. As in the gap example, Oracle and SQL Server reflect this difference in predicate naming. Score will appear as a filter predicate in Oracle and as a regular predicate in SQL Server. Now let's say I have only the index on language, score, and name. With the conditions language equals English and score equals 61, this index is perfect. But if a new query arrives using the condition language equals English and name equals Pinocchio, this index is no longer optimal because there is a gap on the second column. The database can traverse by language, but it cannot continue by name because the next column in this index is score, not name. That means it will read all English rows first and then filter by name, which can be slow. If I want both where clauses to be optimal, language plus score and language plus name, I need two indexes. One ordered by language name and score, and one ordered by language, score, and name. When we talk about multiple queries, we should always keep the number of indexes as low as possible. Let's look at these 4 where clauses with only equality conditions. 1. Language equals English and score equals 61. 2. Language equals English and name equals Pinocchio. 3. Name equals Pinocchio. 4. Language equals English and score equals 61 and name equals Pinocchio. Our goal is to support all of them efficiently with the fewest indexes. Let's start with the shortest, name equals Pinocchio. Because it is a single equality condition, name must be the leading column to get an index range scan. So we need an index that starts with the name. If I then add language as the second column, I also satisfied the second where clause without a gap. Language equals English and name equals Pinocchio. Now for the first where clause, language equals English and score equals 61, with equality on both columns, the database can traverse with the either order. So an index on language and score works, an index on score and language also works. The fourth where clause with all 3 equalities would work with all of these 3 indexes. For the first index, I just need to add score, and for the other 2 indexes, I need to add name. Since score is smaller than name in terms of bytes, I decided to use the first index. I would add the name to the others only if where clause number 2 and 3 were used very frequently, and my priority was to keep this index as small as possible. Before we close today's episode, here are the key points to remember. Index range scan, also called index seek, can be used as long as your where clause includes the leading column of the index. Additional equality columns improve navigation only if they follow in order in the index prefix. Any equality after a gap is used just as a filter, not for traversal. If your index prefix has more than one column, the order doesn't matter for a single equality condition. For example, language and score works the same as score and language for just one query. However, when you have multiple different where clauses, the order suddenly matters. The goal is to design your indexes so they support multiple queries while keeping the index count low. The most dangerous trap is when only part of your equality filters is in the index prefix. The database will traverse only with the prefix columns, and any equality columns after the gap will be used just to filter out rows that have already been read. That can increase the number of rows significantly. A similar trap can happen with include. Even if the columns are physically in the index, include columns are not part of the ordering and are not used for navigation. Include helps with covering, not traversal. So the rule is simple. For equality conditions, always check that every equality column you care about is in the ordered index prefix and in the right order for the queries you want to optimize. So, to wrap it up, equality indexing is all about the prefix and how well it matches your filters. That's it for today's episode. Equality filters may look simple, but now you know how to avoid the traps that can silently slow your queries down. Thank you for watching. I hope this helps you build better indexes in your own systems. In the next episode, we'll go a step further. We'll look at inequality predicates, cardinality, and selectivity. Stay tuned. And if you want to follow the full indexing journey, make sure to check out the playlist and subscribe for the next episodes. Thanks again. Take care.